Next, greedy algorithm on divide and conquer. World, we use algorithm for problem-solving techniques. The importance of algorithm cannot be undermined. Algorithm is solely responsible for driving technical revolution in the past decade. Algorithm depends upon the time and space complexity. Good algorithms take less time and memory to perform a task. In algorithms, there are the two main factors which is time factor. Time factor is measured by counting the number of key operations such as comparison in the sorting algorithm. The last one is space factor. Space factor is the space is measured by the counting maximum memory space required by the algorithm. In creating an algorithm, we can use this five problem solving, which is exemplify, pattern matching, simplify and generalize, base case and build, data structured brainstorm. When we say exemplify is a high-stake assessment program developed and licensed by ExamSoft that enables exam takers to securely take examination downloaded to their laptop computers by blocking access to files, programs, and the internet during an exam. ExamSoft solution is an internet-based exam delivery system. This is the in creating the example of algorithm, before thinking about the logic of algorithm, we should understand the question clearly. Write at least two examples indicating input and output. This 2-minute initial work will remove the misunderstanding. The question is to find first the repeated character in the string. Example. The input is Aleph is ism. The output I, open and close parenthesis, small l. Example number 2. Input love yourself and the output is small letter v. This is the one. Pattern matching. We have to consider what problems the algorithm are similar to. We need to figure out if we can modify the solution to develop an algorithm for the given problem. For example, a sorted array has been rotated so that the elements might appear in the order 3, 4, 5, 6, 7, 1, 2. How would we find the minimum element? This is not called a sorted array because when we say a sorted array, it is a smallest to largest or largest to smallest. So this say what did you say in the screen? They say that has been rotated. So we need to arrange this into a sorted array. 1, 2, 3, 4, 5, 6, 7. That is called a sorted array. Similar problems. Find the minimum element in an array. Number 2. Find a particular element in an array or binary search. Finding the minimum element in an array is unlikely to be useful here, as it does not use the information provided that the array is sorted. Binary search could be very useful. We know that the array is sorted but rotated, so it must proceed in the increasing order, then reset and increase again. The minimum element is the reset point. Comparing the first and middle element 3 and 6, we know that the range is still increasing. It indicates that the reset point must be after the 6 or 3 is the minimum element and the array was never rotated. We can continue to apply the lesson from binary search to pinpoint this reset point by looking for reaches where left is greater than right, that is, for a particular point. If left less than right, then the range does not contain the reset. If left greater than right, then it does. Number 3. Simplify and generalize. Changing constraint. size, length, data type to simplify the problem. For example, changing the data type from double to int. Make the problem smaller, write algorithm for nth data type, and then generalize for double. For example, question is to trim the white space in the password string or squeeze the string. So like this. Number 1. Delete string. Remove white space from the extreme left. Number 2. Right trim. Remove white space from the extreme right. Number 3. Remove white space in the between the string. Number 4. Base case and build. This approach is most widely used in the recursive algorithm. Solve the algorithm first for a base case, just one element, then try to solve it for element 1 and 2, assuming that we have the answer for element 1, then try to solve it for elements 1, 2, and 3, assuming that we have the answer to elements 1 and 2. For example, question is to find all possible permutation of a string, assuming all the characters in the string is unique. Input string which is A, B, C, D, E, F. Solving problem. Take one character at a time from the input string. Base case. A first element of a string is A. A is the first element of string. So A should AB, AB or BE, EBC, EBC, ACB, BAC, BCA, CBE, CAB, ABCD, ABCDE, ABCDEF. The last one is data structured brainstorm. This is tied sum method and based on hit and trial method. Simply run through a list of data structures and try to apply each one. For example, question, numbers are randomly generated and stored into an expanded array. How would we keep track of the median? Odd number of elements, the middle number, but if number of elements, then the average of the middle two elements. Data structured brainstorm. First, linked list. Linked list is not performed very well with assessing and sorting numbers. Hence, it is better to avoid it. Array. Not sure as we already have an array, it could be expensive to keep elements sorted in array. We will keep this option on hold and return to it if it is needed. Binary tree. It can be a valuable option since binary trees do fairly well with ordering. As we know, the top of the perfectly balanced binary search tree is median. If there's an odd number of elements present in the binary search tree, but if there's an even number of elements, the median is actually the average of the middle two elements. The middle two elements can boot at the top. This is probably we need to look at let's hold of it too. HEP. A HEP is really good at basic ordering and keeping track of max and mins. Suppose we have two HEPs. We could keep track of the biggest half and the smallest half of the elements. The biggest half is kept in a min heap, such that the smallest element in the biggest half is at the root. The smallest half is kept in a max heap, such the biggest element of the smallest half is at the root. Now, with this data structured, we have the potential median elements at the roots. If the heaps are no longer the same size, we can quickly rebalance the heaps by popping an elements of the one heap, pushing it onto the other. Greedy algorithms divide and conquer. Greedy approximation algorithms. Greedy algorithms do not always yield optimal solutions, but for many problems they do. Sometimes we still want to use greedy algorithms or other algorithms when they do not give optimal solutions. Maybe finding optimal solution is NP. Complete or the greedy algorithm is much faster than an exactly optimal algorithm for the problem. We can sometimes give approximation guarantees. Minus cost, open and close parenthesis, GS less than equal C, cost, open and close parenthesis, OS minus value. Open and close parenthesis, GS greater than equal value. Open and close parenthesis, OS divide C minus C is called approximation ratio. In general, when you try to solve a problem, you are trying to find the best solution from among a large space of possibilities. Some optimization problems are hard unless P is equals NP. We still need to solve them. Relax our notion of solved. Instead of finding a solution GS so that the value open and close GS greater than equals value open and close parenthesis OS for every other solution OS. Just guarantee that GS is approximately optimal with the approximation ratio. Value open and close GS is greater than equal value open and close parenthesis OS divide C minus C is equals 1. Exact optimal larger. What is an algorithm you could use to select the best option if we can select two cookies from the same row or column. A3 to B5. A3 to B5. What number that we need to find? A3 and B5. So, the number that, this is the B5, this is the B5, and this is the A3. Where is the center number that we need to find? The number that we need to find is 99. 99. A5 to B1. Excuse me, B2. A5 to B2. So, A5 to B2, where's the A5? This is the A5. And the B2 is there. So, what number that we need to find? The number that we need to find is number 81. Because the number that they connect is A1 to B2. The center number is 81. Next, A2 to B3. A2 to B3. This is the A2 and this is the B3. The number that we need to find is 74. 74 because A2 to B3. First, we need to back. Para hindi tayo malito, we need to repeat. A3 to B5. A3 to B5. A3 to B5. So 99. 99. This is the 99. A2 to B3. A2 to B3. This is the A2 and this is the B3. So this number is 74. The number that we need to find is 74. So this is the 99. Oh my gosh. 99. And this is the 70. It's not easy. 74. E1 to B4. E1 to B4. Oh my gosh, sorry. I1 to B4. Oh, this is the B4. E1 to B4. The number that need to find is 60. 60, where's the 60 there? This. E1 to B4. The center number that we need to find is 60. 60. 60. And E5 to B2. E5 to B2. E5 there is the number of E5 to B2 is 81. There is an 81 there. This is the center. This is the number that we need to find. Then E6 to B1. E6 to B1. E6 to B1. The number that we need to find is 60. 60. The last one is E4 to B6. The number that we need to find is E4. This is the B6. Where is E4? The number that we need to find is 40. 40. This is the number that we find, which is 99 plus 81 plus 74 plus 60 plus 60 plus 50 plus 40 is equals 404. That is called the sorted array because largest to smallest. Six, 99 plus 81 plus 71 plus 69 plus 45 plus 46 is equals to 414. The 60 will change into 69. What is an algorithm you could use to select the best option if you can select two cookies from the same row or column? 92 plus 78 plus 75 plus 73 plus 72 plus 68 is equals to 458. Immediately benefit versus opportunity cost. Immediately benefit. How does the choice we are making now contribute to the objective function? Opportunity cost. How does the choice we are making now restrict future choices? The grading method usually take the best immediately benefit and ignore opportunity cost. The grading method is optimal. Best immediate benefits outweigh opportunity cost. Hindi tumawa na kay kung sila nagila. Maximum weight by bipartite perfect matching MWBPM approximation ratio. Theorem. Let JS be the greedy solution to MWBPM. Let OS be any set of position that includes at most one per row and one per column. Then total open and close parenthesis G is greater than equal 1/2 total open and close parenthesis OS. How to prove it? Minus f n is equals to 1, then only 1. Proof by induction on n minus f n is equals 1, then only 1 in n. If n is equals 1, then only one choice, so greedy is optimal. Let G be the largest entry of the matrix and say it is in row I and row colon G. Let M asterisk be then open and close parenthesis N1 minus B minus open and close parenthesis N1 minus 1 matrix where we delete through 1 and row G. Has at most one element in a row I and one element being colon G. G is greater than equal A and G is greater than B, so G is greater than equals 1/2. Open and close parenthesis A plus B minus GS asterisk is equals GS minus G is the greedy solution of OS is equals OS minus EB is another solution. Let G be the largest entry of the matrix and say it is in row I in row colon G. Let M asterisk be the n minus 1 GS is equals GS minus G is the greedy solution for M asterisk and OS asterisk is equals OS minus E and B is another solution for M. So total GS is greater than equal OS. Total GS is equals G plus total GS is greater than equal 1/2. Open and close parenthesis E plus B plus 1/2 total. Open and close parenthesis OS asterisk is equals to 1/2 total OS. Traveling salesperson problem. Starting in their hometown, a salesperson will conduct a tour in which each of their target cities is visited exactly once before returning home. Given the pairwise distances between cities, what is the best order in which to visit them? So as to minimize the overall distance traveled, one of the most notorious computation tasks and NP minus complete search problem, NP stands for non-deterministic polynomial time. TSP result is optimal tour. Note that removing any edge from traveling salesperson tour leaves a path through all vertices, which is spanning tree. Cos TSP is greater than cos of this path. Is greater than equal cos MST. MST is minimum spanning tree. If we can use each twice, then by the following shape of the MST, we end up with a toy that visits all the cities, some of them more than once. Visiting multiple cities not legal. To fix this, the first case in a city is about revisit, moving directly to the new city in its less. Distance of the triangle inequality. This open and close parenthesis UV is less than equal D. Open and close parenthesis UW plus D open and close parenthesis WV. So this bypasses only make the overall tour shorter than illegal tour. 2 asterisk cos TSP is greater than equal to. Cos in ST is greater than equal cos of this tour greater than equal cos TSP greater than cos MST 2. Cos TSP is greater than cos of this tour. Many jobs requiring time Tn need to be divided between two identification machines. We want to complete the job as clearly as possible, so want to minimize the jitter of the two total times of jobs assigning to the two machines. For example, if times are 11, 7, 6, 5, 3, 4, we could give one machine 11, 3, and 8. So 11 plus 3 and plus 4 is equals to 18. The number 6, 5, and 7 is equals 18. Both would finish in 18 times steps. Greedy algorithm. Sort the job times from longest to shortest in order assign each job of the machine with less load sorted 11. So M1 is 11, M2 is 0. Optimal finish. What is lower bound on OPP? total is t. Max of is greater than equal 1/2 total. So 2 of is greater than equal total minus of greater than max. So 2 of is greater than total, of is greater than max. Theorem GS is less than equal to of proof. Let's say that T1 is the total time on M1 and T2 is the total time on M2. Without loss of generality, let's say that T1 is greater than equals T2, and let's say that job was the last job added to M1. Before job G was added to M1 was the load of M1. T1 is minus Tj, while just job G added to M1. T1 minus Tj is less than. Theorem GS is less than equal of. Recall the total T1 and 2 of is greater than equal total. So 2 is open and close parenthesis. T1 minus Tj is less than equals T1 plus T2 is equals Ti. Less than equal 2 of T1 minus Tj is less than equal of. Also recall the optimal greater than equal max T. So Tj is less than equal of, such as T1 minus Tj plus Tj is less than equal to of. T1 is less than equal to of. T1 is greater than equal Tp and Gs. Gs is equal max T1, T2 is equals T1, so Gs is less than equal. In the previous bound, we did not use the fact that we added in the loads in the increasing order of size. Let's say if we can tighten the bound, claim Gs is less than equal G2 of. Let's assume that there are no more than 2 jobs, since if there were only 2, then you could put 1 job in M1 and 1 job in M2 and it would be. Let's only put the biggest 3 jobs in M1 and M2, then the optimal solution will have to put at least 2 of them together. Therefore, T3 plus T3 is less than equal T3 plus T2 is less than equal T3 plus T1 is less than equal of. 2T3 is less than equal of. T3 is less than equal 1/2 of. Now, like before, let C1 be the greedy load for M1 and C2 be the greedy load for M2, and assume without loss of generality that T1 is greater than equal T2. Let job G be the last job added to M1, then since the greedy solution puts job 1 in one machine and job 2 in another machine, G is the greater than equal T. Therefore, by the ordering, Tg is less than equal T3 is less than equal 1/2 of. Then, by the previous argument, T1 minus Tj is less than equal of. C1 minus Tj plus Tj is less than equal of plus 1/2 of is equals 3/2 of. Gs is less than equal T2 of. Divide and conquer. Break a problem into similar subproblems. Solve each subproblem recursively. Combine. In multiplying binomials, if you want to multiply 2 binomials, close and open parenthesis, ex plus b times cx plus d is equals to ec times 2 plus eb plus bc times plus bb. It requires for multiplication ec, ed, bc, and bb. If we assume that addition is has short run time, if we can improve to this by only doing 3 multiplication, which is ec, bb, e plus b times c plus d, and c. Reducing the number of multiplication from 4 to 3 may not seem very impressive when calculating asymptotic. However, if this was only a part of a bigger algorithm, then it may be an improvement. Multiplying binary numbers 1101. 1011 times 1101 times 1. 1101 times 1 shifted once. 1101 times 1 shifted twice. 1101 times 1 shifted thrice. Binary is 140. Time complexity 0 is in 2. Suppose we want to multiply two in-bit numbers together where n is a power of 2. One way we can do this by splitting each number into their left and right halves with each into bits long. X is equals to XL, XR, Y is equals to YL, YR. X is n to the power of n over 2 XL plus XR. X is equals to n to the power of 2 to the power of n over 2 YL plus YR. X is equals to close and open parentheses 2 to the power of n over 2 XL plus XR plus 2 to the power of n over 2 XL plus XR. XL is equals to 2 to the power of n XL YL plus 2 to the power of n over 2 XL YR plus XR YL plus XR YR. Function multiply xy. Input in-bit integers x and y. Output the product x and y. If n1 return to xy, xl, xr, and yl, yr are the leftmost and rightmost into bets of xl and y. P1 multiply to xl to yl. P2 multiply to xl to yl. P3 multiply to xr yl. P4 multiply xr yr. So return to P1 times 2n plus P2 plus P3 times 2n2 plus P4. Correctness. By strong induction on n the number of bits of x and y. This case, n1 then return x, y could make a table of possibilities. Inductive hypothesis for some n is greater than 1 assume that multiply ks x and y returns the correct product xy whenever x has key digits and y has key digits for any one less than equal key greater than n, then by the induction number. R1 is equals to XLYL. R2 is equals to XRYR. R3 is equals to XL plus XR plus YL plus YR. Then, by the induction hypothesis, R1 is equals to XLYL. R2 is equals to XRYR. R3 is equals to open and close parenthesis XL plus YL, open and close parenthesis XRYR. And the algorithm returns to R1 times 2n plus R, open and close parenthesis 3R minus 3-1 minus 3-2 times 2 to the power of n over 2 plus R3 is equals to XLYL times 2n plus open and close parenthesis XLYR plus XRYL times 2n to the power of 2 plus XRYR is equals to XL times 2 to the power of n over 2 plus XR. Open and close parenthesis YL times 2n to the power of 2 over 2 plus YR is equals to XL. Let's see in the runtime of multiply ks algorithm, then Tn is equals 3t and over 2 plus 0 close and open parenthesis n non-recursive part. How Would do you solve a recurrence of the form Tn is equals E T N B plus 0 N D? We will use the master theorem. And that's all. I hope naintindihan niyo.